Hey guys, in this video we're going to cover an example of solids of revolutions using the disk method. So let's take a look at a problem I have here. This is from a textbook called Calculus by Thomas, and this says, find the volumes of the solids generated by revolving the regions bounded by the lines and curves and exercises 17 through 22 about the x-axis. Here I picked just number 22 from this set of examples, or set of exercises rather. And we want to, again, revolve about the x-axis. And we're going to revolve a region. That region is bounded by the lines given from these equations. So whenever you have a solids of revolution problem, the first thing you want to do is graph out any functions and any vertical and horizontal lines that kind of define your region. So note that we have one of our boundaries is the function y is equal to the secant of x. If you recall, the secant of x is 1 over the cosine of x, which you might find helpful in graphing that line. There's a few key points I would note for this graph. One is at x equals 0. So when x is equal to 0, the cosine is 1 there. And so you would have 1 over 1. So in other words, the secant of 0 is 1. Another couple points worth noting are the asymptotes. So whenever you have a function in a denominator, you're going to have asymptotes, vertical asymptotes at x values where the denominator would equal 0. In this case, cosine of cosine of pi over 2 and negative pi over 2 would give you 0. And so we would have vertical asymptotes at those points. So it's worth kind of noting that. And so our function will approach these asymptotes without ever touching it. So it's kind of going to do something sort of like this and like this, while passing through the point where y is equal to 1. Okay, note that the other boundaries that are given here are y is equal to 0, which is just the x-axis itself, and the lines x is equal to negative pi over 4 and pi over 4. So if this is negative pi over 2, pi over 4, negative pi over 4 is sort of halfway in between. Pi over 4, again, is about halfway between. And so by graphing the vertical lines here, and really I don't need to graph the entire line, just everything I need to get the region that we are going to be rotating. And so we can see the region is here. Maybe it doesn't look exactly what you might expect. This is just my limited capabilities, artistic capabilities here. But for all intents and purposes, this will work for solving our problem. So this will be the region that we want to then rotate. And so we imagine sort of rotating the x-axis here. And as we rotate it, this sort of, think of this kind of blade or plane will also kind of rotate around, right? And so think of, if you rotate it 180 degrees, each point in the plane will rotate 180 degrees. So like, for example, this point here will end up down here. This point will end up at a point somewhere around there, let's say. And this point here will end up somewhere around there. And so we can imagine kind of connecting this. And then if it helps you, you can try to picture what this kind of would look like as a solid by kind of drawing in sort of some perspective here. And so you can kind of start to get a picture of the solid here. It's kind of cylindrical looking figure. And what we want to do is find the volume by taking a bunch of disks that would make up this solid and kind of stack them together and take their individual volumes and sum them up. So here we'll just take one representative disk here. And we see that this disk has a center on the x-axis, and it has a radius that is bounded by the height of the secant of x curve above it, right? And so it has a radius r, you could say, but for any given disk along within this solid, kind of like imagine moving it along the x-axis, right? That radius is actually changing, and it's a function of x. It depends on where you are along the x-axis. So the radius is actually the secant of x, right? Also worth noting that the thickness of the disk here will be given by some delta x, right? So you'd have to pick kind of like a starting kind of point for your disk along the x-axis and an ending point, and you can just kind of abstract that away as some delta x. And so next, what you want to do is kind of think about how you get the volume of one of these disks. And we know that the volume of a disk is just like finding the volume of a cylinder, just a really short cylinder, right? So you find the area of the kind of face here, and then you multiply it by the height or thickness of the disk. So for any given disk, let's say it has volume V sub I, right? And its volume will be given by the area of the face here, which is pi, let's call it r sub I, the radius for that, squared, times the thickness of the disk, delta x. Expanding on this, right, this is actually pi. Now, r sub I is given by the secant of x, so we can call it the secant squared of x sub I, delta x. And so what we want to do is take an infinite number of those disks, and we want to find their volumes and then sum them up, right? Now, when we take an infinite number of those disks, what we're really doing is we're shrinking the delta x here. So it's worth noting that the way you would define delta x, and what we're doing, by the way, is we're always assuming that all the disks that we're going to kind of stack together to make this entire solid, they have an equal thickness. So if you want to make them have an equal thickness, what you could do is you could take kind of the starting and ending sort of x values for your solid. And in this case, I know they're pi over 4, negative pi over 4, but we're just going to abstractly call it like a and b. If you want to find the thickness, though, what you do is you do b minus a, so the two endpoints, the difference, and then you divide by the number, n, the number of disks that you want to do. And so what we're going to do to find the total volume of this region is we are going to sum up all the volumes, v sub i's, from, you know, the first disk to the nth disk, let's say, right? But we want to shrink those down. And so what we're really going to do is take the limit as n goes to infinity here. And so when you do that, note that v sub I is equivalent to this expression up here, which involves delta x. And so when you take that limit, you're essentially going to have that limit applying to the delta x, where that n goes to infinity, and this entire term will go to 0. So whenever you have a delta x that sort of tends towards 0, it becomes a dx. And whenever you're taking a sum, by the way, of an infinite number of things, we call that an integral. And so we get the integral from the kind of lower boundary to the upper boundary of, in this case, it's going to be pi r squared, r squared, instead of delta x, it becomes a dx, right? In our particular case, we can fill in what a, b, and r are, right? So a is sort of the starting point is negative pi over 4. B is pi over 4. And as we already stated, r is the secant of x. And so we have the secant squared of x dx. Now, when you go to solve this, before you just jump right in and you might get excited because you might know what the antiderivative of secant squared of x is. Just note we can do something that makes our life easy here because we have these boundaries that happen to be distributed symmetrically across the y-axis, and our sort of barrel, or not really a barrel, but the cylindrical solid here is also kind of symmetrically distributed across the y-axis. So whenever you have this kind of perfect symmetry, you can imagine really just taking the volume of half of this. So you can imagine taking the volume of half of this and then just multiplying that by 2 to get the entire volume, right? Well, that would be equivalent to getting the volume of half of that would be equivalent to taking your lower boundary to be 0. So from 0 to pi over 4. And so this is always something you could do. By the way you can really tell is if you have an even function, and secant of x is an even function, and so secant squared of x is also an even function. So whenever you have an even function, you can do this nice trick. It just makes the math a little bit easier, where you put a factor of 2 out front, and you change the lower boundary to 0. So now we have from 0 to pi over 4. And we also have a pi inside the integral that we could bring out, so I'll bring that pi out. And then we have secant squared of x dx. You may recall that the antiderivative of secant squared of x is the tangent of x. So this evaluates to 2 pi times the tan of x. And we want to evaluate that at the boundaries 0 and pi over 4. And then if you recall how to apply your boundaries, right, you get 2 pi times tan x evaluated at the upper boundary. So that'd be tan pi over 4 minus tan evaluated at the lower boundary, tan of 0. And as you may recall, tan of pi over 4 is 1, and tan of 0 is 0. And so we get our final solution of 2 pi. Okay, I hope you found that helpful, and I'll see you again in some other videos where I do more examples. Thanks for watching.